Hi guys, welcome to our channel of Sciences and Mathematics. Today we are going to discuss a final step or a final set of concepts that we have discussed in thermochemistry. Of course, it's a one step to the final step. Of course, this is going to be on the concept of Hess's Law of Summation. And this is a law which is trying to borrow from the concepts that we have discussed in other videos concerning the coefficients of a thermochemical reaction, or maybe trying to reverse an equation and the effect we are going to have on the concept of exothermic and endothermic kind of reactions. So for this case, Hess's law gives us a combination of this particular kind of concepts, and we're going to see for those equations that can be written in terms of 2 or 3 steps, or which can be represented in form of 1 or 2 steps, how their specific heat or the heat capacity can be able to be calculated. So for that case, without further ado, thank you and welcome. So today we are going to look at the Hess's law of summation, and this law, as I've said, is a law which employs the concept of trying to do a reverse of the equation which we said. Of course, there are some chemical equations which can be reversible, and that one has a consequence on the heat capacity that is maybe involved in the which is either absorbed or evolved during that chemical reaction by changing the nature of that heat, in a sense that if it was exothermic, then reversing that equation, it will be represented as an endothermic reaction. So in this case, we are going to look at one specific example, that is in the formation of an oxide of nitrogen from the combination of ammonia and oxygen, of course, using an equation. So in that case, we shall have an overall equation, and we say that we will find out that this equation can be represented in various steps in agreement with the observation of Hess, which states that in chemical equations that can be written as the sum of 2 or more steps, the enthalpy change for the overall equation equals the sum of the enthalpy changes of the individual steps. So in our case here, we are going to have those 3 equations. I can just round this section of the rectangle. So I can indicate that this is equation 1, equation 2, and equation 3. And the last set of this, which is written, of course, in white, is the overall equation for those combination of equations. Of course, we have not arranged them in the order, but we're going to see on how we can come up with an overall equation from the summation of, or the combination of these 1, 2, 3 steps that are involved in that reaction. So if I may just write this equation on top here, so that we can be able to see what we are trying to discuss. Of course, I write the state here as, and then 5 moles of oxygen gas reacting to form 4 nitrogen oxide plus 6 moles of water. So whatever we are required to find in this set of steps and the overall equation, this is the change delta H. It's what we are required to find. So in Hess's law, the argument is that for a chemical equation of this particular nature, which can be written in terms of step 1, 2, 3, then the enthalpy change, which is the delta H for the overall equation, this one, can be equated as the sum of the enthalpies of the changes for the individual steps. So we are going to have a sum of this after we balance this one and ensure that it's a combination. This combination results in the formation of this equation. Then we are going to have the change in enthalpy, the sum of the change in enthalpy of this representing the sum of this. So Hess's law assists us to find an alternative in trying to find the enthalpy of an equation of this particular nature, whereby we can be able to split this equation in different steps. So fast forward, then we can find the heat of reaction, of course at constant pressure of these individual steps, which have been given as that examples for equation 1. This is change delta H1, delta H2, delta H3. So the argument is, let's denote this one as delta H total. The argument is that delta H1, 2, 3 is the summation, or the summation for delta H1, 2, 3 forms delta HT. So let's try to see what is there on the reactants and the product side. So this is ammonia reacting with oxygen to form an oxide of nitrogen and water. So for us, we will just look at the first product, which is of course a formation of nitrogen oxide. And from our overall equation, we realize that the number of moles, or the coefficient that precedes the nitrogen oxide formula, is 4. So therefore, for us to have a balanced equation for that set of formula, in order for us to get that, then we will see whether the products which are forming on this side and on this, or the reverse of that equation, to get of course a product is going to assist us get to those ratios, mole ratios that we are talking about. So for instance, for us to get the 4 volumes of ammonia which are reacting on the reactant side, we look at the equation from these steps that result in the formation of ammonia, which of course is equation 2, which has got 2 volumes of ammonia produced from this particular equation. And we talked about the effect of coefficients on the heat that is generated. So for us to get 4 volumes of ammonia, then we will have to multiply the overall equation by a factor such that it's going to give us the total volumes of the ammonia that is produced. So from this we can see that the coefficient for this is 2. So we shall multiply the overall equation by 2 in order to get a factor that is going to give us the volume of ammonia that is produced in this case. And in this, we can see that from this equation that we've been given in this step is a reverse of this. So the implication is that we are going to have, in this case, we have a evolution of heat. The reverse of this, we are going to have an endothermic reaction, which is going to be positive. So in that case, I'll just explain instead of demonstrating, because we'll have to reverse this equation so that we are in a position to see. So changing this equation, we shall have 2 moles of nitrogen, or 2 volumes of nitrogen reacting with this one times 2 is 6. We said everything times 2, so this one times 2 is 4. This one times 2 is going to give us negative. So this is going to give us negative 184 kilojoules. So for us to obtain the reactants that we are talking about, then we'll have to reverse the equation. For that case, the effect of reversing this particular equation, okay, then we can just reverse this one and try to see what we get. So we shall reverse this one from Hess'S law. We shall reverse this one to find a reactant, which is ammonia. So in that case, we shall have ammonia on the reactant side, which is 4H3 gas, and the product, the reactants will go this other side, where the products come on the opposite side. So we shall have this gas plus hydrogen. Of course, in this case, when we were balancing, it was 3, so times 2, 6. So the reverse of this will give us a positive for this kind of an equation. So we've ensured that we have brought this kind of a reactant, which is ammonia, on the reactant side using the second set of the equation, and that one has had an implication of changing the nature of the reaction from of course the one that was negative to positive. That means the heat was added into the system, or it was taken or absorbed into the system by reversing that equation. So for the first set of this one, we have already seen from Hess's law how we can be able to reverse it. And then let's look at the second step, whereby we have got the production of an oxide of nitrogen. This, from the first equation, we can see that nitrogen reacts with oxygen to provide an oxide of nitrogen, of course. But in this case, we are seeing that the volume that is produced from the overall equation is twice the volume that is produced from this equation 1 of ours. So what we shall do as well, we have this particular product on the product side, so we are not going to reverse the equation. It's only that we are going to multiply the coefficient by the same factor, which is 2, in order to obtain the same volumes which are here. So for this case, we shall multiply by 2, and we shall have 2 nitrogens, 2 oxygens. We are said to get 4, so that one is balanced. So for oxygen, this is 4, 4. And then we shall have this amount of energy multiplied as well by the same factors we said, to comply with the rules that we have already discussed. So we shall have 180.6 times 2, this is 361.2 kilojoules. So that is a positive. So since we have not reversed the equation, that amount of energy will only be affected by the coefficient that we have multiplied by 2. So let's look at another example. So we have seen how this reactant can be able to be demonstrated using equation 2. And then we have seen how these products can be found using equation 1, and the effects on the heat that is generated for delta H1 and delta H2. And then we are going to look at the production of a water molecule, which is 6 volumes. So we shall have also to see the equation which complies with that. Now from our third equation, we can see that it's going to assist us find the product on that other side. But as well, we can see that the coefficients, or the ratio of the coefficients, are different, in that from our set of step 3, this one is a third of the volume that we are going to find from the overall equation. So in that case as well, we are going to multiply equation number 3 by 3 in order to obtain 6 for the 2 volumes of hydrogen that we are seeing this on this side. So we shall have to multiply each side by 3. So this one was just a moment. The third set of an equation was actually not in those volumes, because it has not. Let's try to see when it was initially like this. These 2 oxygens, these 2 hydrogens had to be like that in order for it to have a stoichiometric equation. So this is 4, 4, 2, 2. So that was the initial balancing of that equation. Then we will have to multiply it by 3 for us to obtain 6. So this one is by 3. And then we shall have this one as well, 6. So we have obtained the 2 products on the product side, which is water and nitrogen. But this one as well, since we have affected the coefficient, it's going to affect the coefficient of that amount of energy, and it's not going to have an effect on either whether the equation is exothermic or endothermic kind of equation. So we shall have a sum of 1450, which is 1450 kilojoules of energy, which is heat energy, which is evolved from that. So in this case, we can see that we have represented the reactant and the product in this kind of way. So the argument from Hess's law is that for an equation that can be represented in more than 2 or 3 or more steps, then the enthalpy change, which is delta 1, 2, 3, for the overall equation equals the sum of the enthalpy change for the individual steps. So which means for us to find delta HT, we are going to find the summation of these individual steps and see what value we obtain from there. So if I can be able to do just away with this, since it has assisted us find the H total. So the argument is delta H total equals delta H1 plus delta H2 plus delta H3, which is, I'm going to assume the plus, of course, but we shall, okay, just indicate plus 361.2 plus, just indicate that for the sake of illustrating, plus 184 184 plus minus 1450. So the total is going to be demonstrated in kilojoules, and that is going to give us a sum of negative 905 kilojoules. So the negative delta H will be equivalent to negative 905 kilojoules of energy. So using these various steps that we have said, we can be able to demonstrate that the enthalpy of the overall reaction is equals the enthalpy of the various steps. Following those rules of the coefficients that we have talked about, that is going to affect the change in heat there, change in H, and then reversing the equation will result in the overall change of the nature of the equation if it was nature of the reaction if it was endothermic, then it will change to exothermic. So I hope those concepts are well understood. And in Hess's law now, we can be able to demonstrate this kind of a summation using a diagram that is going to show the reactants and the product, and that is going to be our final step in illustrating the concept of Hess's law of summation. So let's use an example of what we have discussed already. So we shall have this one as that, and then at this point, okay, can as well do away with this, since we already know that we are dealing with Hess's law. So for that case, I'm going to have that, and then so let's have that diagram there. So we can use a diagram to demonstrate this law, whereby whereby in this case we have the products that were formed. That's an oxide of nitrogen plus 6, that is 4 gas. And then we have the reactants, which is 4 volumes of ammonia plus 5 volumes of oxygen. So this is known as the enthalpy diagram that is used to demonstrate Hess's law, and it's trying to show the overall. Of course, this is the figure that we found after trying to do that combination, and the reverse of that arrow means that heat was taken away from the system, while the product of formation of this one resulted in the heat taken into the system, this one and this one respectively. So for that case, we're going to see that this one demonstrates the amount of heat that is being used, and this is the overall heat that we are talking about there. So in this case, it is on how a diagram on how we can demonstrate the reactants and the products using Hess's law. So for that, we have come to the end of discussion of course of our concept of Hess's law, which of course we shall find and do more examples on questions or problems which are going to entail thermochemistry. So for that case, for today we shall stop there. So thank you, welcome, and God bless you. Bye.